Yes, hello everyone. So, if you are able to hear my voice and see the shared screen, please type Y. Okay, then we'll start. So, as we said in our previous lecture, we'll now start applying machine learning algorithms to speech processing applications. So, we'll discuss some chief or important machine learning algorithms which are used in speech processing. So, in this week, I hope to cover k-means algorithm, k-means clustering, and Gaussian mixture model. And then we'll cover dynamic time warping, HMM, and maybe deep learning fundamentals also. So, let's start with k-means clustering. So, k-means clustering. So, we discussed in our previous lecture what clustering is, unsupervised learning. We do not have labels for the data. We are trying to find patterns in the data, but we do not have labels. So now imagine let's talk about this speaker recognition again, these tasks, the task of speaker recognition. So we discussed previously that for a particular speaker, let's say for a particular speaker, we have many utterances, many phrases that he has spoken, and from each of them, we extract MFCCs. We discard the silence regions, and we keep only those MFCCs which are belonging to the regions where there is actual speech or voice activity. We discard the silence regions. So every speech signal, whatever phrases here he is uttering, we discussed. We will do MFCCs, delta MFCCs, delta delta MFCCs. So if I take 13 dimensional MFCCs, so for every speech frame we have a 39 dimensional. If I took frame here, frame in this direction, it's a row vector or like this. So now we can club all this data we have for all the speech signals. We can club them together because in speaker recognition we are not concerned about uh, the what is called the context or the timing information. The sequential information is not of great consequence. In case of speech recognition, it is important. In case of speaker recognition or accent recognition or emotion recognition, we are trying to find something hidden in the data, something more intrinsic, something more latent inside the data. And it has the sequence of how the frames arrive is not so important. So we can club all this. This is from speech, this utterance one, and again everything we can club together. So and we have all this we talked about. Let's say overall, we gave an example. Let's say overall we have 1,000 frames, and we have 39 dimensional MFCCs, which includes delta MFCCs and delta delta MFCCs also. So we have basically 39 dimensional features, you can say. We have features, some features which we have taken out for each frame, and there are 1,000 frames that we have been able to collect for this particular speaker. So now we can Mathematically, it's better to represent it like this actually, where it represents the frame number, frame 1, frame 2, frame 3, like that, frame 100, 1000. And this is your dimension, 1, 2, 3, 4, 39 dimensions. This is better. So because this represents each, from each frame we are extracting a vector. From each frame we are extracting a vector, 39 dimensional feature vector. Each frame feature vector of certain dimension d. You can say the individual dimension is 1, 2, d dimension. In case our capital D is 39 in this example. And we can say these frames, there are n frames, 1, 2, n. In our case, we have 1000 frames. And then we use this in a machine learning algorithm. So today we'll discuss about k-means, but before that, let's talk about uh, a little bit of a basics of how we do for this particular task, at least speech recognition, sorry, speaker recognition or accent recognition. How we what is called use the training phase or modeling phase. What are the steps are there? It's better to go through it once. So now you have all this. You have all the data like this. You can say each one is a vector, x1, x2, x3. A vector should be written in bold, but I cannot do it here. Scalars are written in normal font, but vectors are denoted generally by bold or by other symbols. Maybe you can put a arrow overhead or uh, uh, underscore below, something like that. I will use this simple notation. I hope you understand that this is a vector, x1, x2, x3. Like that, we'll have xn. And we can say this is an entire data set. This is the entire data set. This data set contains of n vectors. This entire data set of the speaker, and it has n. There's n. What is called? There are n vectors corresponding to n speech frames. So, and these are the dimensions: d equal to 1 to d. Now imagine we give a short, very unrelated but still a good example. Suppose you are trying to classify different fruits in a basket, a machine learning algorithm you want to implement, and then you have, let's say, based on color and let's say acidity. Just imagine that based on color and acidity, you wanted to, uh, based on this color and acidity, you wanted to classify different fruits. So for a particular fruit, some fruit, particular fruit, I know, maybe let's say mango or something, he found out for different mangoes. The color levels, maybe a particular color only, maybe let's say only the red color you are finding out, and or yellow color, and the acidity. Acidity now will given by pH scale 1 to 7 or 1 to 14, I forgot. pH scale 0 to 14 or something like that, 0 to 14, I guess. On the other hand, color, if you represent in whatever your bits per sample are there, bps generally, 0 to 255, if you have 8 bits per sample, or if you have 16 bits per sample, you see again huge 2 to the power 16 different gradings of color you can do. So let's say 0 to 255. So some are, you found that the color is in some bad mango, you even found 0. Some are 255, some are 160 something. On the other hand, acidity, you are always finding 5, 6, 7 something something. Now there is a huge issue here. So when the algorithm will, machine learning algorithm will train, these numbers are so big compared to these numbers. So indirectly, what will happen is this feature will almost be kind of neglected. Its effect will be not incorporated into the machine learning process. So that is why we need to do something called standardization. What is standardization? Standardization is mean subtraction plus variance normalization. So what will we do? Now this is one dimension of your feature. This is like your x coordinate, y coordinate. If you had more features, z means whatever number, whatever variable you see. These are the variables. These all are your variables of your. This is one particular variable of your feature set. So all this 0 to 0, you take out the mean, mu1, again this mu2, and you find out the variance or standard deviation, sigma 1, sigma 2. And then you deduct the mean. You have another, you do this x minus mu by sigma. That is what you will do. For this variable, you will deduct the mu1 minus mu1. Let's say x1 minus mu1 by sigma 1, x2 minus mu2 by sigma 2 for all the points. So what this will do, this will give you another a revised feature vector or standardized feature vectors whose mean will be 0 and your variance will be 1. You find out why. It's a very simple mathematics. You can find out why that happens. So the standardization is a routine process for any machine learning algorithm. Does not matter what you use. Once you get the features, you always do standardization. And then you submit it to the machine learning algorithm for further processing. So now coming back to uh, the topic. So this is our now the this is what we'll be using on notations. We have a feature set comprising of feature vectors. These are your feature vectors. This is your feature set. Each feature vector has is a n-dimensional data. Each dimension represents a variable or a particular feature. So now we'll try and implement k-means clustering. Let's imagine this is a speaker recognition problem, and we have, let's say, 1,000 feature vectors we have collected from a particular speaker. There's just too much data. We want to make this data more concise. We want to represent this data in a more concise manner. How? By finding patterns in this data. And this is where k-means clustering will come in handy. K-means clustering, and then we will talk about GMM in the coming lectures, Gaussian mixture model. So let's now go to k-means. K. What the K means? There are two words here. K, a number K, and means centers. You know what mean, median, this one. Means actually means the average of a few data points. We call it a mean. And what is K? There are K such averages of a data point, and we'll understand this in a step-by-step fashion. Let's have let's assume your data set is like this. It is a set of numbers, some x1, x2, some x3, x4. Let's say this is just only a set of numbers. These are not vectors, but only a one-dimensional data. Basically, this is a one-dimensional data. Okay, so let's imagine this is 0, or let's put star or something like that. Star, star. But this is your data. It has four data points. You can see they already visually there. We belong to two different clusters. They belong to two different regions. So how do we go about finding the appropriate clusters for them? So imagine, so we have this. So let's say we have two clusters, C1. So our goal is to find what will be the these two clusters, and these clusters are defined by their mean. How are the clusters defined? They are defined by their mean. Which one is cluster one? How do I mean? What is the value for that? How do you find out? What is the representation of the culture? In K means it is the mean of that cluster, mean one. So we decide beforehand by some way. Let's forget the, let's keep aside that question, how we come to know how much should be the what should be the value of K, how many clusters we should choose. Let's say we know there are two clusters, we want to find out those two clusters. We also want to find out these points xi, or let's say x1, whether it belongs to cluster 1 or cluster 2. We also want to find out whether it belongs to cluster 1 or cluster 2. All of these points. This is a task. The task is to find out the mean of the clusters, that is their identification, and we want to associate all the data points that we have with respect to those clusters. Which data point belongs to which cluster? That is the goal of k-means clustering. Now we can do this the same for higher dimensional data. Now let's assume something like this. Again, you see, this is a two-dimensional data. You could imagine we have MFCCs, we are saying 39 dimensional MFCCs, or we could do much more than that. We could even do 60 dimensional and so on. Let's say we are plotting only the first dimensional of MFCC, MFCC 1 and MFCC 2, the first two dimensions of all the data points. So you have this x1 vector, x2 vector, x3, x4. Let's say we have only 4 frames. Let's say so x1 1, x1 2, x2 1, x2 2. x31, x32, x41, x42 is your feature set or feature set for a particular speaker, and this is your x11, x12, x21, x22. So this is how you get. Now here the same thing. Our goal is we'll have to find. You can see there are definitely two clusters here forming. We have to find C1 and C2. What is their how are they represented? What is their identification? They will have each of them, or you can say mu11, mu12, mu21, mu22. The first cluster has somewhere. This is the mean mu11, mu12. The second cluster has mu21, mu22. And we have to correctly, on top of that, associate each of them, each of this to a particular cluster. So we need another, let's say, variable, some r. You can say we need something like for this point x1, we will have this x1, sorry, this r11, r12, where you can see here this point x1 belongs to this cluster 1. So r1 should be 1, okay, and r12, let's remove r12 should be, because it does not belong to cluster 2. You can see x1 is here, r12 should be 0. Similarly, if there were multiple clusters, k clusters, only one of them for a particular point, only it will belong to one of them. The rest will be all is association with our rest will be 0. Similarly, x3, for example, x3 will have is r31 will be 0, r32 equal to 1, because you can see this x3, x4, x1, x2. So this is what we want. If we achieve this, then we have found a perfect solution using the k-means algorithm. That is the goal. So now let's discuss how we go about the process. So I will use simple one-dimensional data first. So let's have something like this. So we chose some mean, some mu1 arbitrarily. We chose some mean mu1 arbitrarily. Similarly, we chose some randomly, we chose a mean. There are intelligent ways of choosing also, but let's forget about it. Let's say we randomly chose two means, and we say that is the identification of our clusters. So uh, let's imagine this is your one mean, and this is your somewhere another mean. Let's imagine like that at the moment. Now this is your x1, x2, x3, x1. Now you can find the distance between the first each of the points you can find the distance between this one cluster and the next. For any point you can find these two distances, or x1 you can find the distance between itself and uh, the cluster 1, and again you can find the distance between itself and cluster 2. And what is the minimum distance? What is the minimum distance out of the two? You assign that point to that cluster. So you will assign xi to the closest cluster. So that will give you your, or let me put this as xn because I've been using the notation n. So Rn k equal to 1 if k is the closest, if ck is the closest cluster. Rest is all 0. So you do this for each and every point. So you do this for each and every point. So at the end, what will happen is after the first iteration, this is your first iteration. So you will find that x1 will be assigned to cluster 1, Rnk, you can define it. X2 will be assigned to cluster 1, and x3, x4 will be assigned to cluster 2. Now, for the points belonging to cluster 1, find their find the new cluster mean. So these are the points belonging to cluster 1. Find their mean. You will get mu1 1, which will be located here. A mu1 mu2 1, which will be located here. So this is a very simple example. I can now give a more sophisticated example. So the more sophisticated example will be like this, or more. If the same data points were there like this, suppose for some reason you chose, yes, this is a C1 somewhere. You chose this is a C1. Sorry, this is a C2, and this is a C1. Just I am giving an extreme case because now what would be happening? Now what would be happening? Or let's change it to a little bit more. Let's say C1 mu1. Okay, fine. Let's put C2 somewhere here. So you can see if you start taking out the distances, then x1, okay, x1 will come to, let's say, it will be assigned to c1, a distance is low. X2, on the other hand, is assigned to C2. X3 and X4 will also be assigned to C2. So then if you compute the new mean after the end of the first iteration, so mu1, 1, it will be obviously only one point is associated with C1. All the rest are associated with C2. So obviously it will be equal to this X1. And mu2 will be just average of these 3 points. So your C1 now becomes this after first iteration, and your C2 will somewhere come here. Now you repeat the process. Now you repeat the process. What will happen is x1, because c1 is x1 and c1 the same, so the distance is 0. Obviously you will find x1 will be again coming to c1. X2 will also now come to c1, because see, c2 is far from the centroid. C2 is far, x2 is far from c2 compared to c1, and x3 and x4 will again come to c2. And then after second iteration you will find that after second iteration, what will you find? You will find this exact centroid that you should get. You will find here c1 is assigned, this x1 and x2 is assigned to c1, and x3 and x4 is assigned to c2, and so mu1 after second iteration you will find from here, and mu2 after second iteration you will find from here. And then you can keep repeating the process, but after that nothing is going to change. This is called convergence. Or very little, in real scenarios very little is going to change. This is the essence of k-means algorithm. First, you randomly, you have a number k, you assign, you have decided that there will be, will this cluster whatever data we have into certain numbers of clusters. We affix that, it's called a hyperparameter. We affix the number k. You can say 2, 5, 10, 32, 64, 512, doesn't matter. That you have to figure out based on heuristics. But anyhow, you assign that number k. We will represent this data using k-means clustering algorithm into k clusters. Then you randomly assign, you start with randomly, or intelligently you can also define the initial means of the cluster. What is the initial means of those clusters? You have defined somehow. Then the process starts. Each data will find its distance from each of the clusters. Whatever is the closest cluster, it will reassign itself to that. So then each of those k clusters will now have a new set of assignment. New, these data sets will be reorganized into or reassigned to all of these clusters. Then you find a new mean of the clusters from those assigned data points. Now you repeat, iterate this process. Keep repeating, keep repeating until convergence occurs. There is no change, basically. The cluster centers do not change at all, or there are other criteria also for convergence. So we can easily again extend this. We'll just visualize this in a two-dimensional two-dimensional plane, something like this. Like this. Just visualize it like this. Let's say the first two dimensions of the MFCCs we have plotted for a particular speaker, and it looks like this. First hypothetical example. So, and in the first zeroth iteration or initialization, initialization. Or let me put another one for convenience, for something like this. Initialization, we have somehow figured out that there are three clusters. So this is the hyperparameter. Every machine learning algorithm has some hyperparameters. These are parameters not determined by the algorithm. See, mean is changed and determined by the algorithm. What is the association to which data point, to which cluster each data point will belong? That is determined by the algorithm. But this hyperparameter is an user input. So this is not modified, or this is not the output of the algorithm. So anyhow, so k equal to 3. Now we have to find out, our goal is cluster 1, cluster 2, cluster 3, mu1, mu2, mu3. Now these are all vectors. Mu1, mu2, mu3, all are vectors now. Because it's a two-dimensional, and you can say mu11, mu12, mu21, mu22. Similarly, mu31, mu32. You have to find out the vectors now, because this is a two-dimensional. More than one dimension we are dealing with now. So again, let's imagine we somehow chose arbitrarily something like this. Maybe I will use a different color now. We chose somehow like this. These 3 points we chose. Now for each and every data point, there are 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. So 17 data points we have. So x1 to x17, if you see. On each one of them are two-dimensional data. So we now find the Euclidean distance. I hope you know what's Euclidean distance. I will not go in describing Euclidean, but x1 we represent this as mu1. Okay, let's say mu1 0, because this is initialization. This is similarly mu2 0, mu3 0. We'll find the distance. This is the notation. This is the notation for Euclidean distance. So three distances we'll find out. because there are three clusters. And then we'll assign x1 to the one which is closest. For example, here you can see initially we chose this mu1, this c1, c2, c3. Okay, this point initially after first iteration will come to this cluster 2. This one might come to cluster 1, something like that. Even this one, this point might be assigned to cluster 2. So it will be a mixture of this one. Then we'll find some of the points. You will find that, for example, it might happen this forms one cluster, this forms one cluster initially, and this forms one cluster after first iteration. Then we reevaluate. After reevaluating, you will find that the C1 has moved here, C2 has moved here, and C3 has moved here. Now each of these points, based on, I will probably use another. So C1 is now here, C2 has come here, C3. So after the first iteration, this has happened. Now all these points you now have to reassign in the second iteration. You can see now this point which was belonging to C2 will now definitely come to C3. C2 has moved here. You can already see most likely what will happen is all these points will come to C2. And C1, you can see all these points will come to C1. And then you find you find based on all the points assigned to the cluster, you find their new means. And then this process continues till you find that this C1, C2, C3 after n iterations, sorry, I should say mu1, mu2, mu3. After n iterations, you say they are not changing at all. Or you can fix the number of value of n, and after 100, I will not iterate more than 100 times, let's say, or 20 times. Or there is another way. You can find out the distance. You see, if your clusters are properly placed, that this distance, the distance that you have, the minimum distances that you have, each point assigned to each cluster will have a minimum distance. That distance will be minimum compared to its distance to other clusters. So the overall distance will be the lowest. You can track that also to determine when you should stop the algorithm. But this is the main concept of how k-means works. So next class we will go through the uh, mathematical formulation of the k-means clustering algorithm, and we will then proceed forward to Gaussian mixture modeling.